Here is a brief history of sound waves. The history of sound goes as far back as the beginning of time, to the Big Bang Theory. The first organisms to hear were probably bony fish with organs similar to cochleae. The history of studying sonic waveforms goes as far back as the 6th century when Pythagoras studied string vibrations. Then, Boethius compared sound waves to water ripples. More experiments were conducted to explore sound, such as finding the speed of sound, showing that it needs a medium to travel, and more related to how ultrasound works, the study of echolocation among bats, or how sound reflections can determine locations of objects. In the 19th through 20th centuries, sound wavelength relationships were explored, including frequency and the Doppler effect. In 1877, the Curie brothers discovered piezoelectric crystals that would be later used in transducers. In 1915, Paul Langevin worked toward using technology similar to echolocation to locate objects in the bottom of the ocean. He invented the first hydrophone. By the 20th century, people had figured out how to create rudimentary ultrasound machines. The first person credited for using ultrasound for diagnostic purposes was Carl Dusek in 1942. From then, more modalities of ultrasound were employed, going from A mode to B mode, spectral Doppler, all the way to 4D technology in the 1990s. The study of sound waves has come a long way since the 6th century. Ultrasound technology is continuously developing with smaller instruments and better images. NASA astronauts are able to diagnostically use it because it's portable and may even use it to virtually visualize outer space in the future.
Ultrasound is a longitudinal mechanical wave. Longitudinal waves transfer energy in the same direction as the particle motion. Mechanical waves need a medium to propagate. The sound originates from the electrical current from the transducer, and the wave moves or vibrates through a medium, either air, tissue, or bone. This medium is composed of molecules through which the sound wave can propagate. Particle compression and refraction causes the wave movement, or the transfer of sound wave through the medium from particle to particle.
This image is a great representation of how the machine sends out the sound wave and interacts with an object that produces an echo and is directed back to the transducer. Acoustic variables are parameters that change in a medium due to the propagation of the sound wave. There are 4 acoustic variables: particle motion, pressure, density, and temperature. Pressure is the concentration of force. Pressure increases during compression and decreases during refraction. Density is the mass divided by the volume. Different mediums have different densities, which will also affect the propagation velocity of sound waves. With a decrease in volume during compression, there is an increase in density. During refraction, there is an increase in volume, which results in a decrease in density. A higher density material tends to have a lower propagation velocity, and lower density material has a faster propagation velocity. The only time density is considered is if the 2 mediums have the same bulk modulus. As temperature increases, particle motion increases. This allows sound waves to travel faster through a medium. The parameters that characterize a wave help us to understand the controls of the ultrasound system and how to improve the image quality while minimizing the risk of bioeffects. The different wave characteristics are frequency or period, propagation velocity, wavelength, and amplitude. Frequency is how often an event occurs in a given time interval that is determined by the source, or the transducer you use. Period is the reciprocal of frequency, or the time it takes for one complete cycle to occur, and is also determined by the source. The diagnostic ultrasound range is 2 to 12 megahertz. Frequency relates the pitch of the sound, high or low. The reason the diagnostic ultrasound range is 2 to 12 megahertz is because the wavelengths are too long to obtain good detail resolution if it's below 2 megahertz. Above 12 megahertz, you can't penetrate deep enough into the body. Propagation velocity is the speed of sound through a medium, and it is dependent on the medium. The closer the molecules, the better the conduction of sound. Therefore, bone and metals conduct sound too well. Propagation through fluid are better mediums for sound waves to travel. Gas is poor because molecules are too widely spread. Gel is used because it's impossible to eliminate the air between the probe and the skin without the gel. Wavelength is the physical distance of one complete cycle, one compression and one refraction. It is dependent on the frequency and the propagation velocity, and therefore an important parameter since it is determined by the source and the medium. Amplitude is the deflection from the mean to peak or mean to trough. It relates to the volume of the sound or how loud or quiet it is. Amplitude decreases as the sound wave travels through a medium. Power is proportional to amplitude squared. So a stronger signal that is generated from a higher output power makes for a better image quality. Keep in mind, this will also increase the risk for bioeffects. Here is an image representation of the wave characteristics. Sound waves interact with different mediums in the body. These mediums include air or gas, fluid, soft tissue, and bone. The closer the molecules, the easier the sound wave transfers from molecule to molecule. Bulk modulus is a change in pressure divided by the mean change in volume. A higher bulk modulus is a stiffer material and a higher propagation velocity. A low bulk modulus is a compressible and elastic material that has a slower propagation velocity. As sound waves travel through the body, there is a decrease in intensity as the waves travel through tissue because of attenuation resulting from interactions in the medium. Absorption is the conservation of the sound beam energy into heat within the medium. Absorption is the dominant form of attenuation in soft tissue, and it increases exponentially with frequency. Reflection is where the machine sends out the wave. That wave interacts with something that produces an echo and is directed back to the transducer, and the machine converts that echo back into an electrical signal to produce an image. Without reflection, there is no ultrasound. Refraction is the bending of a wave at an interface between two mediums. Impedance mismatch is a comparison of two mediums at an interface. Two mediums with the same impedance mismatch will have no mismatch and therefore no reflection and 100% transmission. When the difference between the mediums is very large, there is a very large mismatch, which results in more reflection and little to no transmission. This image is a great representation of how the machine sends out the sound wave and interacts with an object that produces an echo and is directed back to the transducer. Here is an image that demonstrates the path a sound wave takes to create an image.
So how does all of this transfer to our machine? As we mentioned earlier, there are multiple factors that can affect the sound waves as they exit the transducer, go into the body, and then come back to be displayed on our screen. There are multiple different functions our ultrasound machine has. As the pulsar sends out the sound waves, they enter the patient. We call this our transmit beam. As the echoes return to the transducer, we call it our received beam. The received beam then goes into our machine as a pre-processing feature. This is our pulsar and our receiver. Pulsar is the frequency selection and output power, among other things, and then the receiver is what processes our return echoes. It is then transferred to the scan converter, which converts the signals returned from the patient into digital data that the computer electronics can understand. That is how the echoes are converted into an image that we can see on our screen. Another feature that our machine has is something called harmonics. Depending on the type of patient or transducer that you are using, sometimes it is more beneficial to use harmonics. Harmonics means that our pulsar sends out a beam at a lower frequency and returns at a higher frequency, thus giving us an image that is safer for the patient. So let's do an experiment. For this experiment, you will need a cereal box, 2 markers, a rubber band, and an instrument or something to pluck the rubber band with. So what does this experiment tell us? As sound waves travel through the body, they send back sound waves and transmit a picture on our screen. As you change the depth by changing the location of the second marker, the frequency changes and the waves sent back are different than they were before. So what happens when the sound waves entering the body encounter something such as a mass, bone, or a cyst? So what does this tell us? When the sound waves hit an object in the body that has different speeds, such as liquid, air, bone, or solid tissue, the return sound waves are affected. Depending on the two mediums, the sound waves could be absorbed, reflected, refracted, or continue to transmit all the way through. We hope this YouTube video helps you understand how sound waves and ultrasound are used today. For more information, visit some of these websites to get a better understanding. of how sound waves and ultrasound are used today.